sphere has an infinite radius and is concentric with the Earth. They gave this sphere a name, celestial sphere, and we still call it that today. From Earth, it appears to move from east to west, one complete rotation every 24 hours. Over the years, astronomers have selected 57 easily identifiable stars on the celestial sphere for navigational purposes. The rest can be disregarded. In addition, navigators have traditionally used the planets Venus, Mars, Jupiter, and Saturn, the Earth's moon, and the sun. To understand how these celestial bodies are used for navigation, you must first review some basic terminology. Let's begin on the Earth, or the terrestrial sphere, as it is sometimes called. The Earth rotates around an imaginary line called the axis. The intersection of the axis and the surface of the sphere are designated the north and south poles. A plane that cuts through the center of the Earth creates an arc on the Earth's surface known as a great circle. There can be any number of great circles. A plane that includes the Earth's axis creates a great circle known as a meridian. There are an infinite number of meridians, and they all pass through the north and south poles. The meridian that passes through the Royal Observatory at Greenwich, England, has been selected as the prime meridian. It is the meridian used as the origin for measurement of longitude. Longitude is the angular distance measured at the poles from the prime meridian to another meridian, east or west, from 0 degrees to 180 degrees. The equator is the great circle perpendicular to the Earth's axis. It is represented by the letter Q. Latitude is the angular distance from the equator measured along a meridian north or south from 0 degrees to 90 degrees. The great circle distance of the arc along the Earth's surface is called arc distance. It can also be translated into linear distance. 1 minute of arc equals 1 nautical mile, or 1 degree equals 60 miles. Thus, the 90 degrees from the equator to the North Pole is actually 5,400 nautical miles. A point at 45 degrees latitude is 2,700 nautical miles from the equator. Parallels of latitude are lines on the Earth's surface whose planes are parallel to the equator. The parallels are combined with meridians to provide the grid system that helps you position yourself on the surface of the Earth. There is a similar grid system on the celestial sphere. To begin with, there is an axis, simply an extension of the Earth's axis. The points of intersection of the extended axis and the celestial sphere are called the celestial north and south poles. Polaris, or the North Star, is approximately at the celestial North Pole, and the rest of the sphere appears to revolve around it. A plane through the center of the celestial sphere produces a great circle on the surface. Great circles containing the axis are called celestial meridians when they are projections of terrestrial meridians on the celestial sphere. They are extensions of the meridians on Earth. For example, the terrestrial Greenwich meridian, or prime meridian, extends out to the celestial sphere to become what is called the celestial meridian of Greenwich, or the prime celestial meridian. The great circle perpendicular to the axis is called the celestial equator, or sometimes the equinoctial. It is an extension of the Earth's equator. Celestial latitude is called declination. It is the angular measure from the celestial equator, north or south, to a given point on the celestial sphere from 0 to 90 degrees. There are parallels of declination on the celestial sphere similar to parallels of latitude on Earth. When combined with celestial meridians, they form a celestial grid comparable to our terrestrial grid system. Now we must relate the two. First, assume you are at a specific point on the Earth. The point directly overhead on the celestial sphere is called your zenith. Your latitude and longitude coordinates on Earth are similar to the coordinates of your zenith on the celestial sphere. Conversely, every celestial body has a point on the Earth directly below it. This is called the geographic position, or GP, of the celestial body. Sometimes it is called the subpoint. If you were at the geographic position of Polaris, the star would be directly overhead at your zenith, and you would be near the North Pole. Similarly, if you were at the equator and the sun was directly overhead at your zenith, you would be at the sun's GP. This principle applies to any celestial body, the moon, a planet, a star, or the sun. You are at that body's GP when it is directly overhead at your zenith. Now at this point, we must introduce the concept of apparent motion between the terrestrial and celestial spheres. Using ancient man's concept that the Earth is stationary, we imagine the celestial bodies on the celestial sphere to rotate from east to west. The rate of motion is 1 degree of arc every 4 minutes, or 15 degrees every hour, or 360 degrees every 24 hours. This rotation introduces another term, hour circle, to help locate these bodies at a given time. It is a great circle on the celestial sphere containing the axis and a given celestial body. Let's assume that at a given moment, the sun's hour circle is coincidental with the prime celestial meridian. 4 minutes later, it will be 1 degree to the west of the prime celestial meridian. An hour later, it will be 15 degrees to the west, and so on. We have used the sun as an example, but the apparent motion is common to all celestial bodies. Their hour circles are constantly rotating from east to west. The term that describes the amount of rotation is called hour angle. Hour angle is always measured westerly from a reference point through 360 degrees. In celestial navigation, we use 3 specific hour angles: Greenwich, local, and sidereal, depending on the origin of the measurement. The first of these, Greenwich hour angle, is comparable to longitude on Earth, except GHA is only measured in a westerly direction through 360 degrees, while longitude is always measured east or west 180 degrees from the Greenwich meridian. Using the sun as an example, we may measure its Greenwich hour angle at any given moment from the prime celestial meridian westerly to the hour circle of the sun. This angle is referred to as GHA sun. The Air Almanac lists the GHA of the sun, moon, and planets for any date and time this data is desired. The second of the 3 hour angles, local hour angle, is measured from the observer's celestial meridian westerly to the hour circle of the celestial body. If the observer is at 90 degrees west and the GHA of the sun is 120 degrees, then LHA sun is 30 degrees. The LHA of other bodies observed for celestial navigation may be computed: the moon, Venus, Jupiter, Mars, Saturn. But when stars are used for navigational purposes, another reference must be used to determine their position. It is the prime hour circle, the hour circle of the sun at the intersection of its elliptical path and the celestial equator as the sun transits from south to north declination. This is the vernal equinox, the first day of spring. The prime hour circle is called by several other names, but they all mean the same thing: the hour circle through the point where the sun's declination is 0. The angular measure from the prime celestial meridian to the hour circle of Aries, the prime hour circle, is called the GHA of Aries. It is listed in the Air Almanac for every date and time. But what the navigator needs to know, of course, is the GHA of the star he is observing. The GHAs of the 57 navigational stars could be tabulated, just as has been done with the sun, the moon, and the planets, but it would require a monstrous publication. Instead, the navigator uses the GHA of Aries plus the third of the 3 hour angles, sidereal hour angle. SHA is the angular measure from the prime hour circle to that of a given star. This angle never changes. This is important. Remember, stars appear to move because of the Earth's rotation. However, they do not change their position relative to one another. So even though the celestial sphere appears to be moving, the prime hour circle and the hour circles of the stars maintain constant relative positions. So the sidereal hour angles, as well as the declinations of the various stars, are considered fixed. SHA and declination for the 57 navigational stars are listed on the inside front cover of the Air Almanac. The navigator can determine the GHA for any navigational star merely by adding its fixed SHA to the GHA of Aries for the time desired. Now let's sum up. When you determine a celestial body's GHA and declination, you know its geographic position or subpoint on Earth. Then, when you actually take a measurement that indicates your range from the celestial body's geographic position or subpoint, you can determine a line of position on the Earth's surface. To determine this line of position, we will utilize the horizon system, which will be demonstrated in part 2 of this series. When a celestial body's Greenwich hour angle, or GHA, and declination are determined, its geographic position, or subpoint on Earth, is known. Obviously, if from a measurement you find the celestial body to be directly overhead at your zenith, you would know you were at the GP of the body, and your latitude and longitude would be the same as the body's celestial coordinates. But the chances of this happening are very rare. Usually, you are some distance away from the GP of the celestial body. When this situation exists, you are only able to determine a line of position. To determine this line of position, we utilize the horizon system. When we extend a line from your position in one direction to your zenith, and in the other direction through the center of the Earth, out the other side, and on out to the celestial sphere again, we have what is called a zenith-nadir axis. A great circle plane perpendicular to the zenith-nadir axis is called the celestial horizon. In effect, we are creating a new reference system with your position at the center. Great circles containing the zenith-nadir axis are called vertical circles. Now we must determine where the celestial body is on the vertical circle. To do this, you must recognize that the distances of space are so great that light from a celestial body arrives at the Earth in a narrow band of rays that can be considered parallel. From your geometry, you remember that a straight line cuts across parallel planes at the same angle. So an angle observed at the surface of the Earth is really the same as that at the center. Suppose the angle is 0 degrees. The celestial body will appear to be on the celestial horizon. This is just a way of saying that the thickness of the Earth can be disregarded in celestial computations. The measured angle of a celestial body from the celestial horizon is called altitude. It is indicated by the letter H. Altitude, when computed, is called HC. It is called HS when it is sighted through a sextant, and it is called HO when the sextant reading is corrected for instrument and observation error. It is easy to confuse altitude with declination, but remember, altitude is measured from your celestial horizon. Declination is measured from the celestial equator. For example, the declination of Polaris is approximately 90 degrees. But its altitude varies depending on your location on Earth. It stands to reason that the angle of altitude will always be less than 90 degrees unless the celestial body is directly overhead. The farther you move away from the GP of a body, the smaller the angle of altitude. The closer you come, the larger the angle. The difference between 90 degrees and the observed altitude of a celestial body is called co-altitude, or zenith distance. This is an important angle to remember when you begin to use celestial navigation to plot a line of position, because zenith distance can also be expressed in nautical miles on the surface of the Earth. Let's say you have obtained a sextant observation of 70 degrees on a star. You can see that a 70-degree measurement can be made from any number of points. You immediately know that you are someplace on this circle, called a circle of equal altitude. This is the first step toward determining a line of position. To find out how far away you are in nautical miles, merely compute the zenith distance. 90 degrees minus 70 degrees observed altitude equals 20 degrees. Therefore, 20 degrees arc distance separates your position on Earth from the GP of the star. Since 1 degree equals 60 nautical miles, you are 1,200 miles from the GP of the star. To find your precise position on this circle of equal altitude, you must take an observation of another body to determine a fixed position. 2 intersections will be noted, but only one will be near your DR position. A third observation will confirm your actual position. So far, we have reviewed with you the terrestrial grid system and the celestial grid system. They are related by your zenith and the geographic position of an observed celestial body. The GHA and declination of a celestial body can be translated into latitude and longitude of its GP on Earth. GHA and declination of the Sun, the Moon, and the planets Venus, Jupiter, and Saturn are available in the Air Almanac for given dates and times. The GHA of Aries is also given, along with the sidereal hour angles for the 57 stars. We have also discussed the horizon system and how it is used to locate a line of position from the geographic position of an observed celestial body. When you note the altitude, you know you are somewhere on a circle of equal altitude around the GP of the observed body. The technique of actually plotting a line of position depends on the observed altitude of the celestial body. If it is 85 degrees or more, the zenith distance formula shows that you are within 300 nautical miles of the GP, and you can actually plot the circle of equal altitude on the navigator's chart. But if the altitude is less than 85 degrees, and it usually will be, you would need a chart too large to fit in your aircraft. So you must use a different technique. It is called the intercept method, and it will be discussed in part 3 of this series. There are 2 methods of resolving celestial observations to determine a line of position. The first should be used if the altitude of the observed celestial body is 85 degrees or more. Let's say it is 87 degrees. In other words, it is almost directly overhead or near your zenith. The angular distance of the body to your zenith is called zenith distance. In this case, it equals 90 degrees minus 87, or 3 degrees. This can be translated into linear distance on Earth, the distance in nautical miles from the body's geographic position to your position. 1 degree equals 60 nautical miles, so 3 degrees equals 180 nautical miles. To locate your line of position, you must first determine the coordinates of the GP. The GHA and declination of the celestial body can be found in the Air Almanac. They can be translated into latitude and longitude of the GP on Earth. You then locate this point on your chart. With your dividers, you can measure off 180 nautical miles. Then, you can scribe a circle or segment known as a circle of equal altitude. This becomes a celestial line of position. You are somewhere on its circumference. To get a fix, you must take at least one more observation of a celestial body, preferably two. This is a very simple method to locate or plot a line of position. Usually, however, you will be observing celestial bodies with altitudes less than 85 degrees. Bodies whose geographic positions will be hundreds or even thousands of miles away from your own position. Theoretically, you could use the first method to plot your line of position if you had a large enough chart. But obviously, you need an alternate. There is one, and it is called the intercept method. As with the first method, it may begin with an observation with the sextant to determine the sighted altitude, or HS, of a celestial body above the horizon, and a notation of the date and Greenwich Mean Time of the observation. This observation enables you to determine corrected observed altitude, or HO, an important factor you will use in a few moments. Now you begin computations by finding the geographic position of the observed celestial body. This means determining its GHA and declination on the celestial sphere. Then, translating those coordinates to latitude and longitude on Earth. Then you assume a position for yourself on Earth, somewhere near your DR position. In the intercept method of celestial solution, you determine and locate your actual line of position relative to your assumed position, instead of the GP of the celestial body. This involves the solution of a celestial triangle brought down to Earth. The points of the celestial triangle are the celestial body, the celestial pole of the hemisphere you are operating in, and the zenith of your AP. On Earth, the points become your AP, the GP of the celestial body, and the appropriate pole. As you remember from your geometry, if you know the length of two sides and the included angle of any triangle, you can quickly determine the other side and angles. If you know the declination, you know this side. Codeclination, or polar distance of the observed celestial body. 90 degrees minus the declination. If you know the latitude of your assumed position, you know this side. Colatitude. 90 degrees minus the latitude. This angle is the LHA, local hour angle, of the celestial body. It is measured from the celestial meridian of your AP westerly to the hour circle of the celestial body. In this situation, LHA of the celestial body equals its GHA minus the longitude of your AP. If your AP were here, east of the prime celestial meridian, you would add the longitude of your assumed position to the GHA of the celestial body to get the LHA. So if your AP is east longitude, you add the longitude to GHA to get LHA. If it is west longitude, you subtract longitude from GHA to get the LHA of the body. However, in this west longitude situation, where the AP is west of the observed celestial body, LHA is this angle. Remember, LHA is always measured westerly 360 degrees. In this case, you can compute LHA by taking the GHA of the body, adding 360 degrees, then subtracting the longitude west of the AP. The remainder is LHA of the celestial body. But back to the first AP we considered and the solution of its celestial triangle. Most of the computations have been done by mathematicians who have created tables designed for three inputs: LHA of the celestial body, whole degree of latitude of your assumed position, and declination of the celestial body. With these three factors, you can turn to your HO 249 site reduction tables to find two important factors. First, the computed altitude, called HC, from your assumed position to the celestial body. HC is the altitude you would observe with your sextant if you were actually at your assumed position. When you have HC, you can compute the co-altitude, or zenith distance, the third side of your celestial triangle. This gives you the linear distance from the GP of the celestial body to your AP. Or, in other words, the radius of the circle of equal altitude from the GP to your AP. The HO 249 tables also give azimuth, the interior angle of the triangle of your assumed position. This angle is referred to as Z. You must then convert Z to true azimuth, or ZN, an angle measured clockwise from true north. A reminder for converting Z to ZN is found in the upper and lower left-hand corners of each page in the HO 249 tables. If true azimuth were plotted on a chart, you would have a line running from your AP toward the GP of the celestial body with a segment of the circle of equal altitude perpendicular to it through the AP. This segment is represented by a straight line because the radius of the circle is so great. With ZN, or true azimuth, you can now begin to locate your actual line of position. You know HC, the computed altitude of your assumed position. You also know HO, the corrected HS, or sighted altitude of your actual position. Suppose these are the actual figures. HO is 45 minutes of angle greater than HC, or, in other words, there are 45 nautical miles difference in radius between the circles of equal altitude, measured along the true azimuth line. But in what direction? Remember the basic principle of altitude measurement. The larger the angle, the closer you are to the GP. The lesser the angle, the farther you are away. In practical terms, if your HO is less than the HC of your assumed position, you are farther away from the GP of the celestial body. If HO is more, you are toward or closer to it. Just remember ho, mo, to. Ho, more, toward. Ho, mo, to. Think of the happy Japanese navigator, Lieutenant Homo-to, smiling over your shoulder. In this case, HO is 45 minutes of angle more than HC. Remembering Homo-to, you know you are 45 nautical miles toward the GP of the celestial body. This is called intercept. The line of position is plotted as a straight line representing a segment of your circle of equal altitude with a barb at either end of the LOP, the name of the source on top, and the time of observation beneath. Two other LOPs derived from observations of two other celestial bodies will give you a positive fix. This is how the intercept method works in theory. We will see how it works in practice in Part 4 of this series. In Film 3 of this series, we examined the principles behind the intercept method for plotting a line of position. Now we will apply the method to actual problems. You need your sextant, a timepiece, an air almanac, HO 249 site reduction table for declination, and an HO 249 site form to record your findings. There are 3 steps required to establish a celestial line of position: observation, computation, and plotting. The sequence of these steps may be altered depending on which of 2 approaches you select. In the pre-computation method, computation is made for a predetermined time. Then an observation is made at that time, followed by plotting. But we'll use the post-computation method with the observation first. In our example, let's assume an observation was taken on the sun at 1630 GMT. Record your observations on the site form. Body, sun. GMT 1630. Date, 24 January. HS of sun, 32 degrees, 21 minutes. Normally, several corrections, such as atmospheric refractions and instrument error, will be made to the sextant reading. But in this case, we'll assume no corrections. Thus, HO is the same as HS. Now you're ready for the computation stage. Remember, you will be using tables to solve a celestial triangle. To do so, you will need to know the declination of the observed body, the sun, the latitude of your assumed position, and the local hour angle between them. To begin, you turn to your air almanac. Open to the page for January 24. Look down the Greenwich Mean Time column to 1630 and read off the GHA of the sun, 64 degrees, 26.8 minutes, or rounded off, 64 degrees, 27 minutes. Declination is 19 degrees, 8 minutes south. List GHA and declination on the site form. Here's where the sun is on the celestial sphere, 64 degrees, 27 minutes west of the prime celestial meridian, 19 degrees, 8 minutes south of the equinoctial or celestial equator. This is one point of your celestial triangle. When the GP sun is translated into latitude and longitude on the Earth, you have one point of your triangle on Earth. Your DR position determines another. Let's say your DR position is 27 degrees, 42 minutes north latitude and 97 degrees, 12 minutes west longitude. Since you are operating in the northern hemisphere, the North Pole becomes the second point on your celestial triangle. The third point is your assumed position. It could be the same as your DR position, but since the HO 249 tables are arranged for whole numbers of latitude, you give your assumed position the nearest whole degree of latitude, or 28 degrees north. You use a longitude for your AP that, when added to or subtracted from the GHA of the celestial body, will result in a whole number for local hour angle. Your DR longitude is 97 degrees, 12 minutes west of Greenwich. You are west of the sun. Remember, figuring LHA in this situation gets a bit tricky. Since LHA is always measured westerly through 360 degrees, this is the angle you are seeking. To compute the LHA of the sun, you must first take the GHA sun and add 360 degrees. This gives you 424 degrees, 27 minutes. LHA is this figure minus longitude. The longitude of your DR position is 97 degrees, 12 minutes west. But remember, the longitude of your assumed position should be a figure that when subtracted from GHA Sun will produce an integral degree of LHA. If you use 97 degrees 27 minutes, the difference will be an LHA Sun of 327 degrees. Now you have established your assumed position. 28 degrees north latitude and 97 degrees 27 minutes west longitude. This, then, is your celestial triangle translated into usable components on Earth. You know this side, the co-latitude of your assumed position, 90 degrees minus 28, or 62 degrees. This side is the declination, or polar distance of the Sun, south 19 degrees 8 minutes plus 90 degrees, since it is located in the southern portion of the celestial sphere. 109 degrees 8 minutes. And this is a known angle, 360 degrees minus your LHA, or 33 degrees. Now, with two sides and the included angle known, you can compute the linear distance side and the true azimuth angle, the elements you need to draw a line of position. In actual practice, you never have to draw the triangle itself. All you need are three elements related to it: the whole degree of latitude of your assumed position, declination of the observed celestial body, and the Sun's LHA. The other information you need, HC and Z, is found in the declination volumes of HO 249 site reduction tables. You enter HO 249 with latitude first. Turn to the pages headed 28 degrees. There you have your choice of two tables. One headed Declination Contrary Name to Latitude, and the other headed Declination Same Name as Latitude. Since your AP latitude is north and the Sun's declination is south, you use the Contrary Name to Latitude table. Note there are two LHA columns, the one on the left for smaller angles, the one on the right for larger angles. Use the right-hand column to find 327 degrees. Move across the tables to the column for the whole degree of declination of the Sun, 19 degrees, and you read HC for 19 degrees as 33 degrees 11 minutes. A D, or correction factor of minus 49, which we'll discuss in a moment, and an azimuth angle, Z, of 142 degrees. The D value is the total difference, or change, in minutes of altitude between the declination of 19 degrees and the declination of 20 degrees. The Sun's declination is 19 degrees 8 minutes, so you must account for the extra 8 minutes of declination. You could use a simple interpolation formula. 8 minutes of declination over 60 equals X, the amount of correction necessary, over the D value of 49. Or X equals approximately 6.5, rounded off to 7. However, this formula is more easily solved by turning to correction table 5 in the back of HO 249. Enter the table with the D value of 49 and move down the minute column to 8. The correction value is read off as 7. Since the D correction value had been a minus quantity, 7 should be subtracted from 33 degrees 11 minutes, the HC of an even 19 degrees. So HC for 19 degrees 8 minutes is 33 degrees 4 minutes. This figure should be entered as HC on your site form. Now for ZN, or true azimuth. The upper left-hand corner of the HO 249 page tells how to compute ZN, your true bearing, from Z. You are in north latitudes. LHA is greater than 180 degrees, so ZN equals Z. LHA less than 180 degrees, Zn equals 360 minus Z. In this case, your LHA was 327 degrees, more than 180 degrees. So Zn equals Z, 142 degrees. The lower left-hand corner of the page lists instructions for south latitude positions. Okay, now let's turn back to your site form. Insert Zn. All the other figures should also have been entered. Now all that's left is to compare HC with HO to determine the intercept distance and whether you are actually away from or toward the observed celestial body from your assumed position. Remember Ho-Mo-To, the happy Japanese navigator. His name is printed right on your site form. If HO is more than HC, you are toward the celestial body from your assumed position. HO is 32 degrees, 21 minutes. Less than the HC of 33 degrees, 4 minutes. So you are away from your assumed position. When you subtract HO from HC, you find a difference of 43 minutes, or you are away 43 nautical miles. Now, let's look at the celestial triangle a moment and see what we have discovered. Here is your assumed position. You know it is on a circle of equal altitude from the sun. You also know that your actual position is somewhere on another circle of equal altitude with a radius of 43 miles greater. And you know the intercept distance is measured on a true azimuth line of 142 degrees. Now let's see how this is plotted. Plotting is really very simple. Here is your AP. Lay out a line along the true azimuth, 142 degrees, away from the celestial body. Don't draw the line. Merely use your dividers to scale off 43 nautical miles from your AP. Draw a line at right angles to the ZN line. This is a segment of the circle of equal altitude of your actual position. This is your celestial LOP. Label it with the source above the line and the time of the observation below. One or more additional LOPs will give you a fixed position. Of course, you will have to take the motion of your aircraft and its altitude into account. You will learn how that is done later. Meanwhile, if you understand the principle of the intercept method, you will be able to work any celestial navigation problem. Let's review the key points briefly once more. It all begins with an observation of a celestial body to determine an observed altitude, HO. Then comes computation. The mathematics of the intercept method involve the solution of a celestial triangle brought down to Earth. The points are the GP of an observed celestial body, an assumed position near your DR, and the pole of the hemisphere you are operating in. In theory, if you know two sides and the included angle, you can compute the other side and angles. The mathematics are done for you. All you need to know is the latitude of your assumed position, the declination of the observed celestial body, and the local hour angle of the celestial body. Determining LHA is the tricky part of the problem solving. In a situation like this, where the AP is in west longitude and east of the GP of the celestial body, LHA equals GHA of the body minus the west longitude of the AP. If the AP is in east longitude, LHA equals GHA plus the east longitude. If the AP is west of the celestial body, the LHA is this angle. Enter HO 249 with latitude of your AP, the declination of the observed celestial body, and the LHA of the body. This enables you to find HC, the computed altitude of the celestial body, Z, the azimuth or bearing angle, and ZN, the true azimuth. By comparing HC with HO, you can determine the intercept distance between your actual circle of equal altitude and that of your AP. Remember HOMO-TO. If HO is more, you are toward the GP of the celestial body. With this information, plotting is easy. You have a celestial LOP. With one or more others, you have a fix. With a little practice, you can easily master the principle of celestial navigation to determine your position. And you will always have the reassurance of knowing you can use this age-old navigation